just know that I'm
Got me?
Well, okay, let's start then. Right, so good afternoon, ladies and gentlemen. Welcome to the repeat of the first lecture on the conventional magnets course for the Cockcroft Institute in December 2014. The course philosophy is based upon what is needed in terms of the present situation for the postgraduates. We're going to be looking in lectures 1 and 2 at an overview of magnet technology. Note this is going to be just room temperature magnets, not superconducting magnets. Electromagnets certainly, and then for the first time I've included something on the use of permanent magnet materials to energize magnets, because it's becoming clear that more and more people are interested in using permanent magnet material rather than big coils that use lots of kilowatts and actually produce lots of heat. So the third lecture is going to be on dynamic and AC magnets, which is something of a Cinderella subject, but of course if you think about it, any circular accelerator, any circular machine that is accelerating is going to have a variable magnetic field, so therefore it is a dynamic situation, and this is often not covered in lectures. And then the final lecture, lecture 4, is going to follow on in that ethos, and it's going to include power converters. Not just DC power converters, but power converters that have been needed for oscillating systems such as accelerators. We will not, as I've already said, be covering superconducting technology, and I think that may very well be covered later on in the year, with a specialist in superconducting magnets being brought in to give a number of lectures, but that's very much a matter for the education programme of the Cockcroft Institute. So, what are we going to have in these first 2 lectures? We're going to start off with DC magnets and the basic nomenclature, the dipole, the quadrupole and the sextupole, which all our postgraduates will now be well acquainted with in terms of the latest lectures that they've had, and also what we call higher order magnets. And then we will look into more theory, and we will start with Maxwell's equations, the magnetostatic equations in 2 dimensions, and we're going to start off with no currents and no steel. And you might say, where's the magnetic field going to come from? But in fact, that'll become fairly obvious that that's the way to start, and then slowly add in steel and then currents. And we're going to be looking at the cylindrical harmonics using only the trigonometrical formulation. It's possible to do the same thing, possibly more elegantly, certainly more quickly, using complex equations. But I think the trigonometrical formulation, fairly basic mathematics, is in some ways is more demonstrating the geometry of the magnets. We'll be looking at field lines for dipoles, quadrupoles and sextupoles. We'll be looking at the significance of the vector potential in 2 dimensions. Continuing on, we then at this point introduce ferromagnetic poles. We introduce steel that is going to support the magnetic fields. And again, the ideal pole shapes, the dipole, quadrupole and sextupole. A very important issue, the forbidden harmonics, which means that nature is on our side, and it's going to make it easier for us to design magnets, because there will be forbidden harmonics providing we maintain a decent symmetry, and that makes life easier. We then introduce electric currents. We work out what the Ampere turns are that will be needed in the dipole, the quadrupole and the sextupole, and the coil economics, which will determine actually the size of the coils. It doesn't determine the Ampere turns that go through the coils, but it does determine the cross section of the copper that we need. We then come on to the new issue that I'm introducing for the first time, and that's the summary of the use of permanent magnet materials. Defining first of all the remnant fields and the coercivity, and then the behaviour of the permanent magnet materials, which dominate how you can use them. And then finally, we look at the magnetic circuit, and then an important part of the lecture, the magnet design using finite element software and the FEA codes Opera 2D and Opera 3D, how we judge the suitability of the design, and then what we do at the ends of the magnets. And then finally, the pretty pictures, some examples of recent magnet engineering. And when you get to that point, folks, You can sit back and relax because you've had the lot of it up to that point. So let's start with the introduction. The nomenclature, quite important. Magnetic field in the strictly scientific definition, symbol H, units of amps per meter in SI units. The old-fashioned units were Oersteds. And then we have magnetic induction, or flux density. Symbol is B, units are Tesla, otherwise known as wavers per square meter. But there is a very great danger that in conversation, not just people not involved in magnetics, but also people specializing in magnetic fields and the magnets that generate them, to use the word magnetic field for magnetic induction. And this is a bit sloppy, really. But in fact, I may very well be doing so in this lecture. But whenever it's important, I will differentiate between magnetic field H and then magnetic induction or magnetic flux density. We then have permeability, which you will all be acquainted with. The permeability of free space is mu naught, units are henries per meter. And then what I call permeability, but which I think most likely in honours courses you've referred to it as relative permeability, and that's the symbol mu, and that quantity is dimensionless. And of course I think what you refer to as permeability is actually mu naught mu. But again, we'll make it quite clear which one we're talking about. Magnet types. Now you've already had the lattice lectures, so you're aware that dipoles are needed to bend the beam in a circular accelerator. Quadrupoles focus the beam, and sextupoles correct chromaticity. And it may well be that in some cases you've not yet covered chromaticity, but that is the variation of focus with the momentum of the particles. And we'll perhaps say a little bit more about that when we actually start looking at the sextupoles in detail. We're going to look at the formal approach to describing these magnets mathematically. One thing to get out of the way: the magnet, the dipole, bends uniformly, but there are two types of end. There's the sector dipole, which is shown here, where the ends of the magnets are normal to the point where the beam enters and the beam exits. And then the parallel-ended dipoles, which are, as they are named, the ends are parallel. And the fact that they're curved is somewhat irrelevant. That's just a matter of saving the amount of steel that you put into the magnet. If instead of having to fill the whole rectangle, you just make it curved. So the curvature is somewhat incidental to the behavior of the magnet. But these two types of magnets have different focusing effects on the beam. And it may very well be that this will come into your lectures on lattices, but we'll just make a clear distinction between the two. The sector dipole focuses horizontally, and it's fairly easy to see, isn't it? The beam that is on the outside of the bend travels further through the magnetic field than beam that is on the inside of the bend. And if it's a true dipole and the fields are equal across the whole of the aperture, then in fact the beam with the longer path is going to be bent more, so that particular device is going to focus the beam. Perhaps not very strongly compared to a quadrupole, but it is going to focus the beam. Perhaps a little bit more difficult to understand is the fact that the parallel-ended dipole, whilst not focusing in the horizontal plane at all, because wherever the beam is radially, it's going to get the same amount of bend, but in the vertical plane, at each end of the magnet, there is going to be vertical focusing. And to understand this, you need to look at these diagrams where if the field has got stray field coming out normal to the end of the magnet, the beam is at an angle to that, and so there is a horizontal component, and that is then going to bend vertically. And so what it comes down to is whatever type of dipole you have, be it sector focus, being a sector magnet or a parallel-ended magnet, it is going to focus the beam. And of course you could go for a halfway measure where the angle ends of the dipole are not exactly fitting in with either being a sector or a parallel-ended magnet, in which case you get focusing in both planes. But this focusing produced by the dipoles, which are there principally to bend, have got to be included in the lattice theory and will contribute to the focusing of the particles. So let's start with the quadrupoles and what they do as well. And we know that the quadrupoles produce a linear variation of field across the beam, and the field at the centre of the quadrupole is zero. We refer to that as the magnetic centre, and that should have been covered by the lattice dynamic program lectures. On axis, beam passing through the centre is not bent. But notice that if it's offset radially, as that particular position there, it will be bent towards the centre, and likewise at the negative x it'll be also bent towards the centre. But if you've got a beam that is offset vertically, or a particle that is offset vertically, then in fact that is going to be defocused, and it's due to the very nature of the quadrupole. This is not something due to bad design. This is inherent in the equations for magnetic fields. So in fact no one quadrupole can focus in both planes at the same time. And that again should have been covered in the dynamic talks. But notice we're going to refer to these as upright quadrupoles. So the quadrupoles where the poles are at 45-degree angles. And we'll come on in a little bit to quadrupoles that are not upright quadrupoles. These are the skew quadrupoles, where the poles are vertically and horizontally disposed with respect to the centre of the beam. And notice something straight away, that if a particle is displaced vertically in a skew quadrupole, then it's not corrected vertically, it is actually given a horizontal bend, and likewise beam that is offset horizontally is given a vertical bend. So in fact skew quadrupoles couple the horizontal and vertical beatatron oscillations, and most of the time this is not what you want to do in a particle accelerator. But it may very well be that you've got skew quadrupole fields present in the straights due to stray fields from vacuum pumps or from just electric connections, in which case a little bit of skew quadrupole to counteract that would be very valuable. And then we come to the sextupoles. The sextupole has got a field that varies as the square of the displacement. There is an equation there where by is a function of x squared, a parabola. Off-momentum particles are incorrectly focused in a quadrupole. If they've got too high a momentum and the quadrupole's got a uniform gradient, then it is not going to be able to focus the high and the momentum particles adequately, and the low momentum particles will be focused too much. And that is what we refer to as chromaticity. But the sextupoles are able to correct the chromaticity. So it will be possible to reduce the chromaticity to zero by the right value of sextupoles in the right position in the lattice. I'm not going to say any more about that. Again, this is a matter for the lattice lectures. But chromaticity is a vital part of the design of an accelerator lattice, and sextupoles are a major feature of that. There are still higher order magnets. I've got here an octopole, an 8-pole magnet, and this is the equation in the bottom right hand corner of the variation of by versus x, and it's going as x cubed. So what effect does that have on the beam? And we're now getting into rather deep water here, and certainly something that I don't really want to spend much time on, and that is that the octopole fields introduce Landau damping into the accelerator. Now you could take a whole series of lectures on Landau damping before you finally understand what's going on, but in the simplest way it induces a tune spread as a function of the oscillation amplitude. So higher oscillation particles will have a different tune to the low amplitude oscillation particles. So it decoheres the oscillations in the accelerator and therefore reduces coupling. And this can have a very major effect on the behaviour of the accelerator, a considerable improvement in the behaviour of the accelerator. So now, that's just a brief descriptive cover of the various magnets that we should be looking at, and perhaps covering the sort of information that you've already had from the lattice lectures. Let's start looking at magnetostatics in free space. And by free space we say there's no electric currents and there's no steel present in the domain that we shall be analysing mathematically. And we start with Maxwell's equations, div B equals 0, curl H equals J. And we're going to say in the absence of currents J, which is J is the current density, in the absence of currents J is equal to 0. And then you remember the theorem that the curl of a div is 0, or rather the div of a curl is 0, so that it means that B can be made the gradient of the negative gradient of a scalar potential phi. And we substitute that in the div B equals 0 equation, and we get Laplace's equation, which is nabla squared phi equals 0. Well, again, you could write a dozen pages on the solution to Laplace's equation, but this, I believe, is the general solution. But most of these terms, notice that there's these things in the front, which I think none of these are physically significant. And then you've got these infinite series as well, and you've got series in r to the n, and you've got series of r to the minus n. And this, of course, is all in polar coordinates. But of those, it is only the equations in r to the n and cos theta, cos n theta, and r to the n sine n theta, which are physically significant. And so we've reduced it to the scalar potential equals an infinite series in arbitrary constants jn and kn, r to the n cos n theta, r to the n sine n theta. N is integral, n is an integer, and jn and kn are functions of the geometry, which are still to be decided. But if we differentiate these and get the components of flux density, we have this little lot down here, the equation of B in the radial direction and the equation for B in the theta direction. So what's the physical significance of these equations? It's an infinite series of cylindrical harmonics. They define the allowed distribution of B in 2 dimensions in the absence of currents or of steel within the domain of r and theta. And we need to be very clear that anything that is not compliant with those equations, any variation of B as a function of space of x and y, which doesn't fit with those equations, cannot exist physically. So if a lattice guy comes along and wants you as a magnet designer to design a completely weird shape, the first question is, does this comply with Maxwell's equations and with Laplace's equation? And if the answer is no, the simple answer is then you can't do it. It's not physically realizable. The coefficients of Jn and Kn are determined by the geometry. And that again will be iron boundaries, but iron boundaries that are remote. That means they're outside the domain of r and theta. Likewise the current sources. We can transfer these to Cartesian coordinates. I only put these equations in so that if you're stuck in an examination, and sometimes I set exams involving perhaps octopole magnets, you can easily pick up these, but this is standard, well, it's almost A-level mathematics, isn't it? It's straightforward stuff. And then obviously x equals r cos theta, y equals r sine theta, etc. bx is d by dx of phi, by is d by dy of phi. So this is pretty straightforward A-level mathematics. So we start with, let's choose the n equals 1 field and decide what it is that it describes. And it's no surprise that it describes a dipole field. Here's the equations for br and b theta, and we transfer these into Cartesian coordinates, and we say that bx, it means bx is equal to j1 and by equals k1. And these are therefore just the values of the flux density in the horizontal plane and in the vertical plane. And the total scalar potential is j1x plus k1y. And it's no great surprise that that's what it looks like. Here we have the lines of constant scalar potential in blue. Here we have the lines of flux density in red. For an equation where by is non-zero and bx is 0. But if you take it the other way, where bx is non-zero, you get k equals 0, k1 equals 0, gives horizontal dipole field. So it's like the vertical field just moved round by 90 degrees by changing the values of, by changing which particular constant is equal to 0. So n equals 2 defines a quadrupole field. And here again are the equations for bx and by in Cartesian coordinates. Here's the equation for the scalar potential. And J2 equals 0 describes a normal or upright quadrupole. This is the thing that we've already talked about. Here's the poles, here's the lines of flux density in blue, the lines of constant scalar potential just about red. Yes, they can be seen to be red. And if you have K2 equals 0, it's the same thing, only this time rotated not by 90 degrees as it was with the dipole field, but rotated by 45 degrees. So K2 equals 0 defines or describes a skew quadrupole. So it's not surprising now, you can see the way it's going to fit together. N equals 3 is going to be a sextupole. Here are the equations in Cartesians. J3 gives normal or upright sextupole field. Here's the lines of scalar potential. And notice I've put some polarities here. The scalar potential lines are going negative, positive, negative, positive, negative, positive. And again, it's no surprise that if you change J3 to be non-zero and K3 to be 0, that you will get a skew sextupole. We don't often get skew sextupoles. So summary of where we've got. The dipole is a constant field described by the equations when n equals 1. The quadrupole, a linear variation with by as a function of x for n equals 2. And the sextupole with n equals 3, the variation of by in the horizontal plane, the variation with x, is a hyperbola. Sorry, it's a parabola. Notice that in some circumstances you'll come across an alternative code, and this is often used for lattice programs where bx is normalized to b rho, which is the rigidity of the beam. B is the magnetic field in a dipole, and rho is the radius of curvature in that dipole. So that then defines the rigidity of the beam, and so it's a normalized situation. And this then has a different set of values for n compared to the equations that we've just established. And this is unfortunate that in this particular subject, n is used in a number of different circumstances for different parameters, and we'll come across in a few minutes another use of the letter n for a different parameter again. But in this formulation, the dipole is n equals 0, the quadrupole is n equals 1, etc. And k, this thing here, has got units of meters to the minus 1 for a dipole, meters to the minus 2 for a quadrupole. So if you're using a lattice code, be careful how you define n, because it could be different to the solution to Laplace's equations that I've just been discussing. I want to look briefly at what the vector potential means in these circumstances, and you'll all be acquainted with the fact that vector potential is defined by B equals the curl of A. A is the vector potential, and also that the divergence of A has got to be 0. And so if we expand this, again in 2 dimensions, in terms of x and y, expanding the curl, this equation here, we get this set of partial differentials in the direction of I, the x unit vector, in terms of j, the y unit vector, and also, even though we've said we're just looking in the xy plane in the 2 dimensions, there's a vector here k in the plane at right angles, normal to the xy plane that we're looking at. So I, j and k are the unit vectors. In 2 dimensions, bz is going to equal 0, and d by dz is going to equal 0 as well. So from this little lot immediately we can see that ax and AY must also be 0. And so B is just equal to d by dy of AZ and d by dx of AZ as well. And that's in the direction X and that's in the direction Y. So what we're saying is that in a two-dimensional problem, the vector potential will always be normal to the two dimensions that you're working in. And the values of B are given by these equations here. And that has far-reaching consequences. So A is in the Z direction and is normal in a 2D problem. And notice, if we take the divergence of this, it's going to equal 0. So in fact, we're compatible with the first equation, div A equals 0. Now this is why it's so useful, that in a two-dimensional problem, the total flux between 2 points in X and Y is proportional to the difference in the values of scalar potential at those 2 points, which might sound a bit surprising, but I'm going to prove it on the next slide. So I want you to consider a rectangular closed path, and we do have to go into the Z plane, at least to consider this. So there is a rectangular path in the Z plane. Here's Y, here's X, and there's Z along this particular axis. And we're going to apply Stokes's theorem. Remember, Stokes's theorem is the line integral of around an area is going to equal the curl area integral inside that. And so we've got this point in our two-dimensional plane of x1 and y1. We've got this point in our two-dimensional plane of x2, y2. And we're going to consider, there's a flux density coming down here. We're going to do the integration around this loop, and we're going to do it with respect to a little element. That's that the integration, the line integration is going to be against d little s, and the area integration is going to be using d big S. And Stokes's theorem says that phi, which is equal to the total integral, the area integral of b dot ds, and is equal to the double integral of curl A, is, and this is where Stokes's theorem comes in, says it's also equal to the integral of A dot ds. But A is exclusively in the Z direction. There's no component of Z, there's no component of A in the horizontal or vertical plane. So you can neglect the two ends here, and we just say that A dot ds is equal to lambda, which is the length of this particular rectangle, given by the difference of the vector potentials at those 2 points. So phi is equal to lambda A at x1, y1 minus A at x2, y2. And that is a very worthwhile equation for us to use when we're working on two-dimensional finite element codes, where we want to know the total flux cutting 2 points. We'll come back in a while to see why this is important. So we're going to now bring in some steel to generate our magnetic field. So the question is, what is our ideal pole shape? And you might want to consider this for a minute, because we've already dealt with the mathematical parameter that defines the ideal pole shape. You already know what it is. We've already defined how it's generated and and what the equations are. And you might want to wonder for a minute, what is it? Well, now, let's consider first of all the flux being normal to a ferromagnetic surface with infinite mu. And this again is a standard bit of technology. This is a standard bit of textbook theory, that if you have a high permeability surface here, here's the high permeability, and here's the mu equals 1. If you then do a line integral around here, we're full of line integrals today, because curl H equals 0, there's no currents in here, because curl H equals 0, therefore H dot ds equals 0. Now, if this permeability is infinite, there can be no magnetic field H. It'll all be 0. whatever the flux density B is, with mu equals infinity, H must be equal to 0. And so the line integral on this side of the path will always be 0. So as this path is completely arbitrary, the line integral there must also be 0. So the line integral parallel to the surface is going to be 0. So H parallel to the surface must be 0. So therefore, if there is no magnetic field H parallel to the surface, there can be no magnetic field B in that direction either. So flux is normal to the surface, and flux is normal to a line of scalar potential, because B equals minus grad phi. So the perfect pole shape is a line of scalar potential. We've already defined what the scalar potential variations are mathematically, so we've now already established what our pole shapes should be. The only problem is they need to be infinitely large, which is not going to impress the people that are looking after the money for which we can build our accelerator. Big problem. So here's the equations for the ideal pole. Dipole is y equals plus or minus g over 2, where g is the interpole gap. Remember, we had those lines of scalar potential that were equally spaced across the axis. Quadrupole, xy equals plus or minus r squared over 2, and sextupole is 3x squared y minus x cubed. We've got those straight from the equations that we've already established for the scalar potential. But what are these r's? Well, these r's are in fact the inscribed radii with the origin at the centre of the beam, and which are touching tangentially the centres of the poles. This is for a quadrupole, but it would be exactly the same concept for a sextupole and for any other higher order pole as well. So these are called the inscribed radii. We need to briefly mention combined function magnets. They've been used extensively in particle accelerators in the past, and I think the very first synchrotrons used combined function magnets. Here's one very frequently used combined function. This is a dipole with some quadrupole field in it. And we're just going to look at that briefly for a minute. It's characterized by a field index n. This is another use of the letter n. And n is equal to minus rho over b naught, where rho is the radius of curvature of the beam at the center, pardon me, and b naught is the flux density at that particular point, times dB by dx. So you can see that n is a dimensionless quantity. It's positive or negative depending on the direction of the gradient, and so in one direction it'll be horizontally focusing, in the other direction it'll be horizontally defocusing, and therefore vertically focusing. But at the same time it's going to be bending the beam because there's a finite value of b at the center. Here's some pictures of typical combined function magnets. They're a bit dark. This is a magnet from the old booster for the Daresbury synchrotron radiation source. And you can see it's a sector magnet, and you can now see in the magnet graveyard at Daresbury Laboratory, because the SRS is now decommissioned. And here's a D-type magnet, and you can see that it's a dipole, because there's only two poles, but in fact they've got a significant gradient across them, and because the gap is widening towards the outside, the flux density will be decreasing, which means that the beam on the outside gets less bending, so that is a defocusing magnet. And here is the exact opposite. Here is an F-type focusing magnet where the gap gets smaller as you come towards the outside. So that's the sort of circumstance where a combined function magnet is very useful, perhaps in a booster for a synchrotron radiation source. We need briefly to convince ourselves that we understand the parameters we're going to be using. Here's a diagram of a combined function magnet, and the point is that this is actually a quadrupole off-center. If you go right the way back to this point here, we're going to say that this is a quadrupole with its magnetic centre. If there was steel at this point, the magnetic centre would be here, and therefore this is just a segment of a quadrupole that we've cut out at large x. And here's the definition of x and x naught and little x, and we're going to shift the origin to this point here where we're going to have little x as our independent variable, and that's where big X, or that's where little x equals 0. But these parameters are 0. The large x naught and the big X are 0 back here at what would be the magnetic centre if it were a true quadrupole. And so here's the pole of a combined function dipole and quadrupole magnet, and we have the equations here, and so the pole equation reference to the beam centre is just given by this, and we can adjust R, that's the inscribed radius of the quadrupole. We can adjust R to satisfy the beam dimensions at that particular position. But bear in mind, of course, the central region of the quadrupole is missing. It's just been used mathematically to describe the poles of our combined function magnet. There can be other combined function magnets as well as dipoles and quadrupoles. You can have dipole, quadrupole and sextupole. That's the same thing as I've just shown, with a bit of sextupole field introduced. Just dipole and sextupole for chromaticity control. And you can have dipole, quadrupoles, q-quadrupole, octupole, etc. because we built a magnet at Daresbury for the SRS that had all these things built in. But it was different to the magnets that you've just seen, because you can generate these combined function magnets the way that we've just described by having poles shaped to give the sum of the correct scalar potentials. And they're the ones that we've just been looking at on the previous slide. But the amplitudes of the dipole, of the quadrupole, of the sextupole, whatever it is that you're building in to your combined function magnet is built into the pole geometry, into the steel, into the shape of the steel. And so at set in steel, you can't vary it. There can't be a knob in the control room where you can change the gradient of a combined function magnet with dipole and quadrupole. But the alternative is to have multiple coils mounted on a circular yoke. And then, if you put coils in the right place, you can independently vary the currents to generate different harmonics. And here again, out of the graveyard, Daresbury laboratory, is a 12-pole magnet that we use. We can generate vertical dipole, horizontal dipole, upright quadrupoles, q-quadrupole. The main sextupole in the accelerator was generated by these big coils in the centre here, and it could also do 10-pole and 12-pole, though there was no real reason for that. And in fact, there is a tutorial question that is set at the end of the course, which involves debating where these coils should be and what excitation is needed on these coils to generate all these different harmonics. We're now going to look at the practical pole. We've already said that the ideal pole shape is given by the line of constant scalar potential, which are infinite. But we can't make infinitely large dipoles, quadrupoles, sextupoles. So we've got to chop them off at a reasonable position in XY space. And this introduces higher harmonics, it introduces errors into the magnet, errors which are largely unsatisfactory and not what we want. But here's the advantage, that certain symmetries that we can impose will restrict the nature of those errors. Let's look at the dipole, for example. We've already said that the polar orientation decides whether it's skew or whether it's horizontal or vertical, and that's just given by the line of symmetry, in one case being y equals 0, and in the other case, in the quadrupole, the symmetry is given by x equals 0, around the x equals 0 and y equals 0 axis. But there's an additional symmetry that you can impose by putting the pole edges at the right place. So if your dipole is symmetrical, not just about the horizontal axis, the y equals naught axis, but you make it symmetrical about the vertical axis, the x equals naught axis, then in fact you are imposing a very significant constraint on the geometry of the magnet. And likewise in the quadrupole, in addition to it being symmetrical about the y-axis and the x-axis, if you make it symmetrical about the 45-degree axes, you've got further advantages coming out of that. And these advantages can be seen in terms of the suppression of harmonics, which are given by simple trigonometrical arrangements, by trigonometrical analysis of what's going on. So here's the dipole symmetries. We've already said that we've got to have poles that are equiplaced across the horizontal axis, and that means that this is the positive scalar potential line and this is the negative scalar potential line, and we've had that from the very beginning. But now if we make the poles equidistant in terms of their cutoff from the centre, then we've got equal lines of constant scalar potential here, and in fact even at the cutoff where the scalar potential will be changing, we also still have that symmetry. And so if you put that into the trigonometry, it means that jn's are 0 and kn's, that's the one that defines the dipole field, are non-zero only for n equals 1, which is dipole, n equals 3, which is sextupole, n equals 5, which is tenpole. So for a fully symmetrical dipole, only 6, 10, 14 poles are going to be present. So we've already killed off half the possible harmonic errors that could be introduced into our magnet. So what does it do with a quadrupole? Well, here's the symmetries given by the pole orientations, which is the ones that we've already covered. Here's the symmetries covered by the fact that the pole edges, if we've made the thing a symmetrical quadrupole, are cut off equidistant from the 45-degree lines. And that therefore means, looking at the trigonometry, the kn is non-zero only for n equals 2, which is a quadrupole, n equals 6, which is 12-pole, n equals 10, which is 20-pole. So for the fully symmetric quadrupole, only 12, 20 and 28, etc., with that separation, errors can be present. So things are getting better. And then the sextupoles, we can do the same thing again. We can look at the symmetries due to the pole orientations and then the symmetries due to the pole edges. And we find that the first error in the sextupole is at 18-pole, and then 30-pole, and then 42-pole. And so nature's being very beneficent to us in that as long as we keep our magnets fully symmetrical, we can get rid of an awful lot of errors. And that makes life much easier when we come to build our magnets. So here's the summary of what's allowed and what's not allowed. And you see I've also added octupoles here, and the first error order in the octupole is 24-pole. To be honest with you, that's the point where you barely need to think about it. 20-pole, 40-pole, and it carries on up with that separation. However, we've just been talking about perfect symmetry, and nothing in life is perfect, including engineering, including assembly, including machining. So the magnets that we build will never be perfectly symmetrical. We will want to make it as close to perfect as possible, but there's still going to be errors present. So we're going to look briefly at what errors can be there due to us making the standard tolerances that are available in normal engineering. But let's start first of all with what's called the standard dipole, which is a C-chord dipole. So there's the coils that are exciting the magnet. So here's the steel, and here's the beam center line is down here. And you've got to ask yourself straight away, is this a fully symmetrical magnet about the beam? And the simple answer is no, it's not, because there's a return yoke on the left-hand side, but there's no return yoke on the right-hand side. Agreed, the coils are symmetrically placed, and as are the cut-offs of the poles, but not this back leg. So it does mean that there's going to be some asymmetry present. and providing the permeability, the relative permeability of this steel is very high, it's going to be a very small effect, because essentially it's going to look as if almost this is a symmetrical magnet. The lower the permeability, the worse it'll become. But in the very least, it's going to generate the harmonics that I've just said are going to be absent if you've got a fully symmetrical dipole. It's still going to allow two, and that's a quadrupole. And you can see immediately how the quadrupole could be generated, where the flux density going around on the inside has got a shorter path compared to the flux density going around on the outside. Providing the relative permeability is high, that'll make little or no difference to the flux density down here. But if the permeability drops, then there's going to be a weaker field here to here, and that's going to introduce a quadrupole field. And so even our C-core dipole is not completely symmetrical. What about other errors that can be introduced? Well, here's a dipole that's been made with a slight angle on the top pole. We're only perhaps talking about 20, 30, 40 microns, but it's still going to introduce 2, 4, 6 pole, etc. What about this thing where there's a bit of a hollow in the middle? Again, 50 microns, perhaps. It's going to introduce a sextupole, 12 pole, 18 pole, etc. Quadrupole asymmetries begin to get a bit more complicated. Here, where we've separated the top and bottom poles have been moved apart a bit. Again, we're talking about very small numbers, talking about 50 microns perhaps. That's going to introduce an n equals a negative, n equals 4. It's going to introduce an octupole field. And if it's in the horizontal plane, the octupole field will be there, but it'll be positive, whereas in this case, the octupole field will be negative. And if the top ones are split sideways with respect to the bottom poles, then that's going to induce a sextupole field. And so it goes. If you have the poles moved over at the top at an angle compared to the ones at the bottom, that's going to introduce a skew field, and it's also going to introduce a sextupole field. So whilst we've talked about the advantages of having symmetry in our magnets, the assembly process is critical. It is crucial to try to get them as symmetrical as possible when assembled. And some of these forbidden harmonics are always going to be present when you build a magnet. These errors are bigger than the finite mu errors that I've just dealt with a couple of slides ago. They can seriously affect a machine behavior. They must be controlled, they must be measured. If necessary, you must adjust the magnet to reduce or eliminate these fields. Now, we've been through the basic equations without any steel or current present. We then introduced steel. We now get to the point where we're going to introduce electric currents into our equations. And we go back to curl H equals J, only now J is not 0. And again we use Stokes' theorem. Stokes' theorem is getting quite a bashing, isn't it, today? And what we can say is that if you apply Stokes' theorem to a circular path with the field cutting, with a current here and the field perhaps cutting it in the centre, the standard Stokes' theorem is that V dot ds is equal to the double integral, the area integral of V across the surface. So that is the line integral of this vector V, which can be magnetic field or can be some other vector, around the loop is equal to the double integral, the area integral of the curl of the area here. And you apply that to curl H equals J, and it gives Ampere's equation. H dot ds equals the current that's cutting this loop, which we call Ni, the Ampere turns, because there may be current I in the coil, but the coil is going to have a certain number of turns. So the Ni Ampere turns is the total current cutting this path S. And this is the basic equation that tells us what the currents need to be.
Yeah.
Well, yeah, okay, right here. So we have H dot ds is equal to the ampere turns Ni. So if we go to this and we integrate h dot ds around this, we've got lambda over mu, and we've got g times h is going to equal the ampere turns. And so we have the B in the air is equal to mu naught Ni over G plus lambda over mu, where G and lambda over mu are called the reluctance of the gap and the ion. That's the reluctance of the gap, and that is the reluctance of the ion. And if we can ignore the reluctance in the ion, because lambda may be the order of a metre or so, but mu, if it's a decent piece of iron, should be the mu should be the order of 5, 6, 7, even more thousand. So this is going to be a very small. This is going to be a very small value. So in simple terms, Ni equals Bg over mu naught. That is the equation for the dipole. If we now go to a quadrupole and the sextupole as well, how are we going to work out what the ampere turns that will be needed in the quadrupole? Well, we're going to take a mathematical concept of a very big quadrupole. Here's the cross section, here's the part of the quadrupole that you normally would think about, but we're going to consider the steel going to very, very large x values, so far in the positive x direction that our magnetic field, our magnetic flux density, B, can be regarded as vertical, and the plane or the direction of the yoke to be so shallow that it's almost parallel to the axis. And we then treat that as a dipole. So we've got the pole equation, which is xy equals r squared over 2, and on the x-axis we have by equals gx, where g is the gradient of this quadrupole in Teslas per meter. So at large x, we just now put these equations in. Remember, we've got Ni equals Bg over mu naught. We put that in. Ni equals the B, which is gx, times r squared over 2x, which is this gap here, all over mu naught. And luckily, the x's cancel. Isn't that wonderful? So we have the equation that Ni equals gr squared over 2 mu naught. And that is the ampere turns that is needed per pole. So the fact that we've had to go to very large values of x to establish this has disappeared when our x's cancel, and it applies to any quadrupole function, any quadrupole shape, and any quadrupole magnitude. And for the sextupole, the same method with a coefficient gs gives Ni equals gsr cubed over 3 mu naught per pole. And here's the general solution for any magnet. It just follows the same concept. In this case, we're doing an integration of this line of axis here between the axes, and we're equating this to the scalar potential phi at this particular surface. And the general equation is Ni equals 1 over n, 1 over mu naught, br r to the n minus 1. And this, inside the brackets, is the magnetic strength in Tesla meters to the n minus 1 times r to the n. And that's fully compatible with the equations that we've just established. So I think we'll leave it there, ladies and gentlemen, and I think we'll pick up from this particular point in lecture 2. Thank you very much.